We continue with our look at applications of Gauss's law. Here we have a solid metal sphere of radius r, and it's separated by an airspace from a solid metal shell with the given inner and outer radii. So basically what we have here is, you might say, a cannonball in the middle, an airspace surrounding it, and then a thick metal basketball that is surrounding the outside. And the charges that are on these objects are given. The net charge on the cannonball is plus 3q, and the net charge on this metal basketball that has a very big thickness, positive 5q. How is the plus 3q distributed on the inner sphere at the surface? Anytime you have a conductor in electrostatic equilibrium, any charge has to be on a surface. The charge residing on the inner surface of the shell, that is that surface right there. What is that going to be? Well, that, and we'll explain this later, is going to be the opposite of whatever the charge is here. So that is going to be negative 3q. And why don't we preview this just a little bit? If we were to draw a Gaussian sphere inside this thick metal basketball, what do we know about the electric field magnitude at that location? Isn't it 0? And if the electric field magnitude at that location is 0, by Gauss's law, that must mean that the charge enclosed is 0. And if the charge on this cannonball is plus 3, then the charge that is on the interior surface here must be negative 3. Plus 3q on the cannonball, therefore it has to be negative 3q on that side, because inside here the electric field has a strength of 0. So the enclosed charge within such a Gaussian surface has to be 0. The charge residing on the outer surface of the shell, well, the net charge is plus 5. And on the inside, it's minus 3q. So on the outside surface, it must be plus 8q. Let's determine the electric field for various values of little r. First, when little r is inside here, we said that all of the charge on this cannonball is at the surface. So for r less than big R, the electric field has to be 0. Anytime we're inside a conductor in electrostatic equilibrium, that electric field has to be 0. Similarly, let's skip directly to R between 3R and 4R. In other words, within the thickness of this metal basketball, inside a conductor in electrostatic equilibrium, the electric field has to be 0. What about between here? Like, let's draw a Gaussian surface in between here, and I'll call that little r. Let's use Gauss's law to figure out what the electric field is outside the cannonball, but before we get to the inner surface of the basketball. So let's use Gauss's law. Here we go. Q enclosed divided by epsilon naught is equal to the integral of E dot dA. Now, what's the charge that's enclosed in our Gaussian sphere here? It looks like the charge that's enclosed is plus 3q. That's it, whatever's at the surface of the cannonball. So I'm going to change the numerator on the left side to 3q. The electric field magnitude is equal everywhere, so that integral can be moved over to there. And when we integrate dA for that Gaussian surface, it is 4 times pi times little r squared, which means that for big R less than little r less than 3r, The electric field is going to be 3Q over 4 pi epsilon naught r squared. All right, what about out here? When little r is bigger than 4r, we do the same thing. We're going to use Gauss's law again. Q enclosed over epsilon naught is equal to the surface integral of E dot dA. What's the charge that's enclosed? The net charge that's enclosed, you can look at it two ways. You can say, oh, cannonball has a net charge of plus 3Q, and the basketball has a net charge of plus 5, so that's plus 8. Or you can say the outer surface of the cannonball is plus 3, the inner surface of the basketball is minus 3, but then the exterior surface of the basketball is plus 8. In either case, the charge that's enclosed is 8Q. The electric field magnitude is equal everywhere, so we're going to integrate dA, and when we integrate, what's the surface area of a sphere? It's 4 pi little r squared. And what's our electric field equal to then? Well, it looks now like it's 2Q over pi epsilon naught r squared.